Alright, so starting another video here, looking at our first section in chapter 2. So this is looking at particularly measures of spread, and now looking at how that applies to distributions. So we're going to look at one particular measure of spread known as the standard deviation. Now, the way to understand, now your book will give you like the formula on how to calculate standard deviation, but you do not have to know the formula. What is important is to understand the concept, how we get the number, but really we won't ever have to manually calculate the standard deviation. Our calculators will do it for us. So I'm just going to take a moment to kind of explain what is meant by standard deviation, and then talk about how we get it in the calculator and how we can then use that to then help us describe data points in a distribution. So in front of us here, I have kind of like this data set. So in the middle, I marked here where the location of the mean is. So now what we want to start to do is to get used to symbology. So when we talk about the arithmetic mean, there are two symbols that you are going to come across. There is the Greek letter mu, and then there is this symbol here, the X with the bar above it. Both are the mean, but they are for different things. So for right now, as we start stats, we're going to look at everything in the population. So this is known as the population mean. But as we progress through the course, we're not going to be able to get everything from the population. We're going to take a small representative sample of that population and calculate the mean of that smaller group. So that X bar would stand for the sample mean. But for right now, we're going to focus on, or assume that whenever we get information, it's coming from everything in the population. So that would be this Greek letter mu. So here I have the Greek letter mu standing for my mean. Now these other lines are indicating points that were in the data set. So I see that some points, all these points vary in different ways from that center point. So some vary, some vary a long distance away. Some are actually closer. So all these varying distances from the mean, so like here, then you got this over here, some vary above, some vary below. So what the question then becomes is, okay, well, if I'm going to measure spread, I would say on average, how far away is a point from the mean? So how far away, on average, are we going to be away from the mean? And that is what standard deviation means. Okay, so standard meaning, okay, we're going to standardize, we're going to average those deviations. Okay, now how you calculate that, so standard averaging, I would add up all of these deviations, not the data points themselves, but how much they're varying from the middle. So some vary above, some vary below. So I would take each data point and subtract that from the mean. So, if it's in front, so it would be, so here's my data point, and subtract it from what the mean is. So let me start putting it as capital mu. So this would be, and I'm going to sum up all those deviations. So this would be the deviation from the mean. And I'm going to add up all those deviations, however many there might be. So I'm going to put, this is, from 1 to, and there's an infinite number, maybe, of data points, or there's, sorry, not infinite, but a finite number of data points. So this would mean, I'm going to add up all my data points, and then since we want an average, I'm going to divide by the number of data points that there are. But if I just leave it as this right now, the problem is, well, what if some vary below So these would be considered negatives. So if I had a bunch of positives and negatives, they might cancel out and therefore tell me that the points don't vary from the mean. So we need to deal with what happens, what do we do with negative deviations? And the way we handle that is to measure the absolute deviation, the distance we are from the mean, okay? Not the literal value away from the mean. So that'll deal with the fact of looking at negative deviations. So this is the formula for standard deviation. Now again, you don't need to calculate it by hand. Our calculator does it for us. So I'm going to pull up the TI calculator here, and I'm going to share that, and I'm going to put in some data points. So let's say I'm just going to do something simple here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, let's go back here. 10. All right. So I'm going to go ahead. So now here's how we calculate standard deviation. We've already done it, actually. If you push the stat button and go into the calc menu, and under 1var stats, we're going to calculate the one variable statistics for this list of values. So I see X bar, which we said stands for the middle. So yeah, 5.5. So from 1 through 10, the middle number would be 5.5. The standard deviation is reported in two places. So there's this capital S, and then there's this Greek sigma. So the Greek sigma stands for the population standard deviation. The capital S stands for the sample standard deviation. So again, we're hearing those terms of population and sample. We will deal more with sample as we progress through the course, but for right now, we're going to deal with things as the population. So we're going to look and grab the number that we see under the sigma symbol. So 2.872. So I'm going to go back to my whiteboard and I'm going to write over here. So for my data set 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, the mean was 5.5 and the standard deviation was 2.87. Oops, forgot the other digit. 2.872. Okay, so what does this number mean? So what this is telling me is that on average, a data point will vary from the mean by 2.872. So what's the meaning behind that? This is how we can now tell if another data point were to appear, is it something that should grab our attention? So for example, if I were to grab the point and let's say, oh, I was the guy that got a 6. Let's say these were exam scores. Oh, I was a person that got a 6. Well, that's higher than the mean, but is it higher? Did you deviate more than average, or did you just have an average deviation? Well, according to this, 5.5 plus that 2.87, so you would have to vary. So this is within that one standard deviation, right? So if I do 5.5 plus the 2.872, our value of 6 is within that window. So even though it's technically above the average, it's not that you deviated far enough. But if I were to say, hey, I got a 9, well, a 9 deviates, more than that average value. So that is something that is of note. So that means that that score is somewhat more significant than the person that scored a 6. Vice versa, what if somebody scored a 4? Well, you scored below the average, but it's not really like you deviated that far away from the mean. So this is why when you look at grades, it's like, oh, well, I got an 83. Well, I got an 84. Well, we both get then the same grade. We both got a B. Why is it the value that you have to go so far in order to get, let's say, a B plus or an A minus, it's because now you are going beyond what would be considered an average deviation. And the further away you go, the more out of average that is, the more significant it is. Hence, when it comes to grades, it's like, well, if the average score was a 50 and you got 100, well, that's really far away from the mean. So this is where, when we measure spread, we want to consider, okay, well, how does the population look like when we collect the data? Is everybody closely packed together? So then that means small movements away from the mean could equal to much higher significance. But if the data is very spread out, then you really have to make inroads to kind of make yourself significant, either one direction or the other. So the way that we measure this deviation is known as a Z-score. So let's take our continued example here. So let's say, okay, I got that score of a 9. So how far away is that from the mean? Well, I could take my 9 and say, well, 9 minus 5.5. So that's going to give me a 3.5. But now what I want to do, so this 9 is 3.5 units away from the mean. This is our deviation. Okay, so I took my data point and I subtracted it from the mean. So we are 3.5 units away from the mean. But what was the standard deviation? So now what I want to do is take that standard deviation and I'm going to standardize this distance away from the mean. So if I divide it by the standard deviation, so now I'm going to we'll go back to my calculator here for a second. So I'm going to go 3.5 divided by 2.872. I now get this number, 1.21, and I'm going to round it off, so 1.219. Okay, so 1.219. So what does this now number mean? So I took my deviation and I divided it by the standard deviation in this line here. So what does this mean? We are 1.219 standard deviations from the mean. So now, if we're within one standard deviation, that would be considered the average. So we can clearly see, yeah, a 9 is significant. Why? Because it is more than one standard deviation away from the mean. The further away we get, we can see that this number is going to become larger. But if I were somewhere closer in, so let's say I take that 6 and I want to calculate the Z-score. So let me label that here. So what we calculated right here, this is known as it's called a Z-score. Okay. You can think of this as a standard score. Because what we're doing is we're standardizing the distance. I'm no longer just going to, baldly look at that 3.5. I want to standardize it. How many deviations am I away? So if the data was really spread out, this would be a big number. But this number in comparison to the standard deviation, that's where we standardize the scores. Okay, so now let's say if we had, so the example of let's say the 4 I had said. Okay, so 4 minus 5.5. So that would have been a negative, negative point, having a little meltdown here, so negative 1.5, sorry. So 4 minus 1.5? Oof. See, this is what happens when you take a break from Labor Day. Yes, negative 1.5. All right, so now this is again my deviation. So again, what does this number mean? Okay, I am 1.5 units below the mean. That's what this is saying, 1.5 units below the mean. Now, what do I want to do? I want to standardize that. So, okay, is that significant? Is that, is that more than the average deviation? Well, I'm then basically comparing it is to this. So now I would, in my next step, go, oh, I'm going to take this number and divide it by 2.872. So if I do that, and again, go back to my calculator. So I'm going to divide by 2.8, whoops. 2.872. Now you see I got a negative 0.522. So this is a negative 0.522. So what does this number mean? This is telling me I am 0.522 standard deviations below the mean. So since this is still within 1, yeah, then the score you got was less than the mean, but would we consider it noteworthy, significant? Not really, because it's within that window. So this is where, again, it's like, oh, I got a bad quiz score. Does that mean you're a horrible student for the entirety of your academic career? No, we know that, oh, well, tomorrow, maybe I woke up on the wrong side of the bed, I stayed up too late, extenuating circumstances out of my control. If I take it tomorrow, same test, I know I'll do better. Yeah, that happens. And you guys see it when you take SATs. Sometimes, oh, I went to this one sitting, I got a great score. I went the second time, now I went down a little bit, and then I went a third time, now I went back up. So there's variation due to other elements. So this standard deviation allows us to say, well, okay, we know your score might go up and down on any given day, but did it go up or down significantly? And that's what we want to address when we calculate Z-score. All right, so that does it for our quick little explanation of standard deviation and Z-scores. We're going to be calculating this quite a bit throughout the course, and actually throughout this whole chapter 2 as we progress further. So again, if you like this video, please make sure to hit a like and subscribe to the channel, and I will see you guys on the next video.